Hi, everyone. Welcome to the Tea Time talk today. I will introduce one of my recent work on a block coordinate formulation of mean-variance optimization. And this work is in collaboration with a bunch of guys who cannot be here. Tengyang Xie, who's a UMass guy, Yangyang Xu, who is an optimization guy in RPI, and Mohammad Gavanzadeh and Nilam Chao, who are the Google DeepMind guys in California.
Mohammed used to be here.
Yeah, he used to be here 3 years. Yeah. Yeah, he planned to visit here in early August, he said. Yeah. So I will split this into two parts. The first is the background, and the other is the mean-variance optimization. So first, I will introduce several technical ingredients of the background, which are double sampling, coordinate descent, and convex conjugate with another name, Fenchel dual, with another name, Legendre transform. The reason why I introduced the three names of it is that because someone writing papers saying that I come up with a convex conjugate, and another year passed by, and another guy saying that I come up with a Fenchel dual. The third year, the other guy said I come up with a Legendre transform. Okay. So first is the double sampling. Double sampling problem is that originates from the very basic statistical property that the expectation of a product does not equal to the product of expectations unless the two variables x and y are independent with each other. And what does this mean in reinforcement learning and Markov decision process? If you are studying the deterministic MDP, then things are golden. You don't need to worry about anything. But if your Markov decision process is in general, it means that it is not in a deterministic environment. For each state, if you take an action, there may be multiple successful possibility of successful states. Then you need to worry about this if x and y are both dependent on the successive states. This implies us what? This implies us if the x and y are both functions dependent on the successive states, you need to sample twice. Or at least at each step, you need to generate two independent trajectories and sample from each independent trajectory. This is usually problematic in our general reinforcement learning settings. Since in general reinforcement learning settings, we always assume all we can obtain is a single trajectory. And we need to learn from this single trajectory. Only two cases you don't have the double sampling problem. The first is that you have a generative model of the transition kernel. And the other case is that your environment is deterministic. But in general, for single trajectory, and we are learning from stochastic environment, we always have these double sampling issues. That comes a great deal of Y residual gradient proposed almost 30 years ago. Is a standard stochastic gradient algorithm. It converges in all scenarios. Okay. But it's not very welcomed in real applications, is that because it has the double sampling problem.
Residual gradient.
Yeah, the residual gradient. Yeah. So first, I'll introduce the stochastic gradient as a very quick recap. So stochastic gradient is trying to, please.
30 years ago? Residual gradient was 30 years
Oh,
ago?
sorry. It's 25 years ago. Yeah. Stochastic gradient methods are the first choice for large-scale machine learning proposed by UAlberta, and it's considered as the first choice in large-scale machine learning nowadays. The problem it tackles can be considered as a bow, and each time you go along the direction of the bow, and this descending direction is the unbiased estimation of the true gradient. The benefit of the stochastic gradient is that it has a much lower computational complexity than computing the true gradient. So thanks to the merit of randomization, it actually can reach much better, especially in the initial phase performance, than the true gradient. So a very commonly used way that for large-scale problems in industry level use, you first use stochastic gradient. And then once you are sure it has approaching the optimal point, you switch to the quasi-Newton method to reach better convergence rate. This is often commonly used recipe in industrial level applications. And now, I will jump to the block coordinate descent. To do this, let's first have the last glimpse of what stochastic gradient trying to solve, minimizing over the objective function, which is convex, like a bow, and a single variable x.
Wait, what is G and what is F?
Oh,
G is a bowl function, right?
yeah, J is the ball function, and yeah, I should make system on the
F is the ball.
yeah.
What is G?
The gradient.
So sorry.
G is the gradient.
G is a true gradient, and F is the sorry, F is the true gradient. G is just the unbiased stochastic estimation of it. So computing the gradient of F is usually very computational costly, and that's why we computed G, and G is a unbiased estimation of nabla F, of the gradient of F. And what if our objective function does not have a single variable? It has have two variables or even more variables. And like this, each variable, we call it coordinate. So what if the objective function has multiple coordinates, minimizing over x and y, and the fxy? So the objective function comes into this. To make a distinction, I change from the uppercase J to uppercase L. And there are two methods solving it. The first method is that in each iteration, you update each coordinate, meaning that you update each variable, x and y, in a cyclic manner, like this. First, you update x, and then you got the xt plus 1. Then you update the y. Remember in here that the x has been already replaced, updated to xt plus 1. This is in a cyclic manner, means that in each iteration, each coordinate is updated. Another case is that each iteration, I do not update all of the coordinates. I just randomly pick up one coordinate and update it. And I go to the next iteration. In next iteration, I randomly pick up another coordinate again and update it. In this case, in each coordinate, in each iteration, I only update one coordinate. Usually, these two methods are like close friends, shaking hands with each other, co-lived for over 20 years. Why? Because both of them have their benefits to different people. Cyclic BCD method usually have better empirical performance. But the randomized BCD method is usually easy to conduct theoretical analysis. So if you are an engineer, you may prefer more on the cyclic one. But if you are writing papers, you may prefer the randomized one because it gives you a much easier time and your hair drops down much faster. Yeah, because today in the morning I washed my hair, I find that I really dropped down my hair. And now here comes to the convex conjugate, and another name Fenchel dual, another name Legendre transform. And these are the two pictures I found online. Actually, it turns out that the Fenchel is, Legendre is on the left. He's a mathematician with 300 years history. And it turns out that Fenchel is much younger than I thought. He is a German mathematician and who lives just in the 20th century. So a convex function can be represented as follows. Fz equals to max of the inner product of z transpose y minus f star y. And f star y is called a convex conjugate function. And specifically, if fz equals z squared is a quadratic function, then we have the very simple formulation as follows. Z squared equals to max of y 2 times zy minus y squared. In the scalar case, even a primary school pupil can deduct this because it's just from the x minus y squared is non-negative. And if the primal problem is a maximization problem, then we have what? We have the BCD problem, maximizing over fzx equal to maximizing over two variables, x and y, 2zy minus y squared. And if the primal problem is a minimization problem, what do we have? We have the primal dual set point problem formulation, minimizing over x. Minimizing over x is zx squared equal to minimizing over x and maximizing over y, 2zy minus y squared. Please.
If this is important, let's go through it more slowly, because I didn't understand anything on this line.
Okay.
Beginning with the first line.
Mm-hmm. So, okay.
Any convex function can be represented in this way? Is that what you mean?
Yeah, yes.
It's a kind of a funny way to represent any function, any convex function. Why is that? What is f star?
The f star is defined as the maximizing over y and z transpose y minus fx. Oh, well, if I have a pen here. The f star of a function is defined as the maximizing over y transpose x minus f y. And
so what? I understand all the symbols in that formula.
Mm-hmm.
But what is it conceptually? Convex conjugate.
Well, conceptually, the convex conjugate is like that. If you have a function, not necessarily convex, and that means if it's not necessarily convex, that means it's epigraph. Its epigraph is not necessarily convex. Then how do you construct a function where its epigraph is a superset?
What's an epigraph?
Okay, the epigraph is if it is smaller than a z, then it is the area that is above, that is below this line and above this function. Or I can explain it in another way, is that given two variables, x and y, we all know that this quadratic form is non-negative, right? And if you expand the left hand side of it, it is x squared. If I write it to be more general in the vectorized formulation, it should be like this, right? Okay, then right, and if I times I do not have. So this can be replaced by what? Can be replaced by because this equal sign. If this equal sign cannot be taken, then this should not be max. It should be inf. Oh yeah, sorry. So should be sup. But indeed, this equal sign can indeed be taken when x equals y. So we are confident that this max can be right as here in very confidently. And in this way, we can say that if it is an inner product of itself, then it has an equivalent formulation of max over y to x transpose y minus y transpose y. So,
And that's f star of x?
and this is the f star y, and this is fx. Simply put, if fx has this formulation, then the f star y is itself, but they do not always equal to each other.
You see there's, for any f, there's always an f hat which has its property. Theorem or something like that? Yeah.
Yes, right. So clear on this? Yeah. Yeah, actually, I don't think I need to introduce Fenchel dual and the Legendre transform, but some papers introduce a new notion and say that they created this stuff. Okay. So if you look at the bottom line.
So you just proved that any x transpose x can be written this way.
Yes, right.
But here you say any convex function. And x transpose x.
That is a generalization of the whole formulation.
There's a theorem that says that.
Yeah.
Any function that is convex and always continuous.
Right. Yeah. Yes. Yeah. I should be. Yeah. Extension problem. It had to be continuous as well. Yeah. And if you look at the bottom line, that is actually fits into the nice formulation of the gradient TD algorithm, because they can be reformulated. Both GTD and GTD2 can be formulated as a set point. Please.
So really, you've proved the third point.
The third 1, 2, 3. Okay.
Yeah, because that's for a quadratic function simply true.
Yeah.
Now
Sorry.
you talk about the primal problem.
Okay.
So you have to explain this word primal.
Oh, primal is the primal problem is the original primal. Consider primal as another word because we live in a world constituted of two types of people: the ordinary normal people and the mathematicians. So there are indeed some mathematic guys. Okay. So whenever we say a word history, those math guys will say something like filtration and something like that. And whenever we say something like original, and the mathematics guys will say something like primal. So primal problem is the original problem formulation. So when I say primal, is that, for example, in this slide, sorry, I cannot. Sorry for that. Let me try.
You can point at the slide.
Yeah. Okay. Sorry for my mistake. Okay, it's here. When I say primal, is that if your original problem is a maximizing over something or minimizing over something.
Maximizing, finding the maximizer for f.
Yes, right.
That's what they mean as the problem.
Yes.
The original problem is maximizing. Then we're doing a max of a max.
Yeah. A case example is that the original problem formulation may be different from its primal dual problem formulation. For example, if your original task is to maximizing the money you earn, this is the original problem, or called the primal problem, is to maximizing the money you earn. It's a maximization problem. It turns out that its dual is to minimizing the mistakes you make. So now, the dual problem is not a maximizing problem anymore. It's a minimization problem, minimizing the mistakes in investment you make. So the original problem is a maximization problem, and the dual may not be maximization. It becomes a minimization problem. And in this case, the primal is a maximization problem over a single variable. It turns out that its dual is maximizing a problem with respect to two variables, x and y. And if the original problem is a minimization problem, it turns out that you can convert it to an equivalent primal dual problem of minimizing over something and maximizing over another thing.
So these second two equations are using the equation above them, and that's only for quadratic problems.
Yes, right.
So we're only talking about quadratic.
Yeah, we only talk about the quadratic case.
Well,
Please.
question.
Mm-hmm.
And I think a lot of these things come from this, is that what you need to do is sort of cut to the chase of what problem in reinforcement learning or problems in reinforcement learning you want to solve, and back up and show us the details of how it's solved. Because for those who don't have the vocabulary that understands, you're losing them right away.
Oh, yes, right, yeah.
So if you can say, here are the problems you want to solve, and P.S. these methods will solve them, and P.S. here's how these methods work.
Okay.
So you may have slides in there, but I would say maybe go to the end of your talk.
Sure,
We've
okay.
had this problem before in here. You may want to go to the end of your talk and almost work backwards. I mean, I'm not saying that I haven't seen your slides, but that might be a way to, because it's already 20 of them, and I don't know what people have. Some people I know have time constraints. And
Right, yeah.
So I don't, but I do know that some people do. So you might want to do that because we're not very far in, and it's already at that time. So.
Right, okay. Yeah. This is a good suggestion, and I will go to the problem. The problem is that, remember in reinforcement learning, the basic problem is that we want to maximize the cumulative reward. And if you consider risk, for example, which is a very common concern in investment, you don't want to be too aggressive because you don't want to take the risk of going bankrupt. And in that case, that becomes a mean variance optimization. You want to, in this part, you want to maximize the expectation of the sum of reward, which is completely the same as our standard reinforcement learning problem, with an actual constraint that the variance should be smaller than a threshold. The variance is a very powerful way of describing the risk. And this is a composition between two functions. So, and the mathematicians has proved that this problem is actually an NP hard problem, and it's very intractable to solve. So why is it hard? That if you convert this constraint problem to its Lagrangian dual, like this, turning a constraint optimization to an unconstrained optimization, and compute the stochastic gradient like this, you will find you will have three terms to compute. The gradient of J, the gradient of M, and the product of J times the gradient of J. J is the expectation of the sum, and M is the second order moment of the sum. Computing the gradient of J is very easy to do, and computing the gradient of M is very easy to do as well. But computing the third one is not easy to do because both of them involve the successive state. And in this case, as we just introduced about the double sampling, we cannot have an unbiased estimation of it from a single trajectory. So this is where the bottleneck is. And the previous methods by Tamar and Shime and Ort's group, they use the two-time scale method. So previously, as by Hamid Mai's paper, whenever you have a double sampling problem, you introduce an auxiliary variable that operates at a lower time scale, at a faster time scale to estimate something. You need to compute from the second trajectory. This is a very successfully used technique. So either you sample twice, or you create an auxiliary variable which operates at a faster time scale that estimates the thing you need to estimate from the second trajectory. And I adapted these 2 slides from Muhammad's tutorial here, so the notations may be a little bit different. And he used 2 ODE equations to estimate J and the gradient of J, and in turn, he can avoid the double sampling issue. But one thing that we have in mind is that 2 time scale method, they require a very stringent requirement on the time scales. One should be quasi-stationary with respect to another one. And in real applications, it's very difficult to satisfy this assumption, and you need to tweak the step size quite often to obtain a satisfactory result. And the other disadvantage is that these 2 time scale techniques originates from Konda over 20 years ago, is that it can only provide a asymptotic convergence guarantee, meaning that, okay, given the time is infinite, your final solution will definitely converge to the optimal one. But how long is this trajectory? You don't know. You have no idea about that. And motivated by this, I want to kill 2 time scale, not kill, avoid, and shake hands with him and say bye, I don't want to see you again. And the block coordinate reformulation can help us. Using this quadratic formulation we have introduced here is that we can turn the original problem to a maximization problem as its dual. And in turn, the maximization problem of f lambda is equivalent to the maximizing over 2 variables, theta and y. And it is now in the block coordinate formulation. So after you reformulate this as a block coordinate formulation, you can either use the stochastic gradient like this, the cyclic coordinate ascent like this, where each time you update both y and theta, and randomized coordinate ascent, each time you either update theta or you update y, just based on the result of flipping a coin. So remember that the stochastic gradient ascent algorithm treats the theta and y as a variable, and you update them. And the cyclic coordinate ascent treats them as 2 variables. Each iteration, you update both of them. And the randomized coordinate ascent, you need to have a coin to flip at each iteration. And the benefit is that you don't need to update all the 2 variables. You just need to update 1 variable. 1 variable is enough. The algorithm is like this. So the first boast I have made is that I do not want to use 2 time scale. A single time scale would be good enough. And that's true. And the second boast I have made is that I want to provide a finite sample analysis. Different from the set point case, actually, when I look into the optimization literatures, it seems that these guys are too lazy to provide a finite sample analysis to it. And so this is the weapon we created on our own, but it's definitely non-trivial. It really costs us a lot of time of providing this finite sample analysis to theorems for the general block coordinate problems. And after we proposed that, we applied to our algorithm, and we come up with this result. Removing the concerns of the constant factors, this theorem implies us that if constant step size are chosen, then the sample complexity is 1 over epsilon square in order to find epsilon stationary solution. So once again, I emphasize a little bit here. The analysis tool we designed here is really takes a lot of time to propose it. And the experimental results we compare with the Tarman's 2 time scale method, and the 3 method we propose is called the stochastic gradient algorithm, the randomized coordinate descent, and the mean variance policy gradient. We call it MVP to give it a kind of a nice name, and the vanilla reinforce the policy gradient. because we only we do not want to get involved any of the value function estimation. So any kind of actor-critic algorithm, such as the TRPO or A3C, is not considered to be compared in this paper to make a fair comparison. We only compare the vanilla, the pure policy gradient algorithm. And remember, the results is not actually Gaussian. We use Gaussian to approximate just for better illustration. The more it is on the right, it means that the more accumulative reward it can obtain. And the higher this peak is, it means the less variance it is. So the ideal case is that it is at the far right, and it is in a very, very skinny and is very tall. So you can see from these three domains, the portfolio domain, the American option domain, and the optimal stopping domain, both are very standard domains for the risk-sensitive comparison. And you can see that the red curve, which is our major selling algorithm, is that it can reach both small variance as well as reaching high cumulative reward, meaning that you are indeed making some money, and you are also reducing the risk for that. And on the contrary, we would like us to see the green curve, which is Tarma's two-time scale method. First, it is, according to our hands-on experience, the step size is really very, very difficult to tune. Even if we spend a lot of time on tuning it, you can see that its best performance, indeed, it can reduce the variance because it's still very tall, but its cumulative reward is not as satisfactory as our proposed method. So I'm sorry, really sorry that it runs out of time. So our take-home advice is that by reformulating the mean variance into a block coordinate ascent algorithm and use the cyclic block coordinate ascent algorithm to solve it, it can indeed reach much better performance than the previous two-time scale method. And meanwhile, you avoid the problem of tuning the step sizes. Yeah, thanks for attending, and sorry for running over time. Thank you.
So you're showing curves here,
Mm-hmm.
as well as individual points. What is this really being shown here?
Yeah, because this is a standard way of showing the risk-sensitive point, because the true ones are just data points, and if we illustrate the data points, the illustration result will be very bad. So a commonly used method is to use the Gaussian to approximate the data points, but in reality, it is not a Gaussian distribution. We just use the Gaussian to better illustrate the cumulative reward and its variance distribution. But in fact, it is not Gaussian.
Where did the curves come from? The points come from empirical.
Yeah, from running. I think it's from running 200 experiments per domain and per method. But it's not that time costly because, for example, the first domain, the portfolio domain, it only has 7 discrete states. Sorry, it only has 11. It only has 11 discrete states, and this optimal stopping domain, it has only 7 discrete states.
These graphs are representing a table of numbers where you have mean, final performance, and variance, and each is displaying it this way.
Yeah. Yes. So yeah. As Adam said, the other way of showing it is to show it via a table. The first column is the method. The second column is the mean. The third column is the variance. But we just want to use graph to. Yeah, remember that in fact it is not Gaussian. We just use Gaussian to fit the curve to make it illustrative. Yeah. Thank you for explaining that. Yeah.
About the other objectives, because the mean variance doesn't really satisfy the risk measure definition, right? The variance is not a good objective.
You mean objective? You mean mhm.
Axioms for being risk measure.
Oh, you mean other risk measures such as value at risk or?
Because the mean variance is not a risk measure.
Yeah. For that, we did not show it because I asked two guys, both are experts in this field, Muhammad and Merrick. Merrick urged me to show all the results. Then I plot a bunch of figures and put them into the appendix. And Muhammad says you don't need to show them because your objective function is just mean variance. If you his original words is like this: if your primal problem is the mean variance, if you show your method rocks on var, for example, value at risk, that means you are just lucky. And I don't want to give them an impression that I'm just lucky, so I remove all this. Because I think it is pretty reasonable because my objective function is just the mean variance. If I show the performance on other risk measurements, such as var and and the Sharpe ratio, because my objective function is not that. If I perform well, that just means that I'm in luck. So I did not show the illustration on Sharpe ratio and var and other things.
Okay, do you mean? I mean, you can. I'm not sure. Can you apply the same method to solve those? Probably there's still some issues, right?
Yeah, there are still some issues. This.
Approach to optimize with respect to risk measure.
Yes, right. Yeah.
You have performed the experiment for risk measure which you don't have this guarantee. Is that what you mean?
Yeah, other risk measures cannot be easily use this block coordinate reformulation. Only the mean variance.
But you experimented on them.
Yeah. So the experiment is to show the measures of the mean variance objective function. Yeah. Oh, please. Yeah.
I guess the primal problem is a constrained optimization problem. And once you find its Q problem, is that still a constrained optimization problem, or is it unconstrained?
Oh, once you use the Lagrangian dual, you are turning a primal constrained problem to a primal dual unconstrained problem.
You don't have any constraint on the Lagrangian multipliers?
No, the constraint, the original constraint. Once you use the Lagrangian multiplier, it switches from a constraint to a multiplier. So in that case, the primal constraint problem disappeared, and instead, what shows up is a set point of the dual problem. So it is minimizing over the primal variable and maximizing over the lambda, which is the auxiliary dual variable controlling the Lagrangian multiplier.
Your dual variable should, like, for example, it should be greater or equal than 0. Like that lambda.
Yeah, right.
And you can deal with this problem in your algorithm block. Sorry.
Yeah, it can deal with it's for in short, you can deal with it. Okay. Yeah, that's a good question. Yeah. Please.
You mentioned actor critic, and you didn't compare to it. So, is there a way to incorporate like the value estimates of actor critic into this algorithm in a similar way as actor critic, or is it just like totally unapplicable? I didn't really get a look at the algorithm side.
I do not quite follow. I do not mention actor critic. Actual critic.
When you were presenting your results, you said we did.
Oh, actor critic. Yeah.
Because it uses value estimates. But is there a way to incorporate?
Yeah, there's a way to incorporate that because that can be make an analogy to Tamar's paper and Muhammad's paper. Because once you add the critic, you are adding an actual time scale.
Right.
So in that case, Tamar's paper in 2012 is a 2-time scale, and Muhammad's paper 2 years later or 3 years later is a 3-time scale. 2-time scale is a nightmare for you, and 3-time scale is a nightmare for all of us. Yeah. So so once you add the actor, you are adding one more time scale. So this method can be incorporated with time scale. In that case, it will change from a single time scale to time scale. Yeah. You're welcome. So thanks for attending, and sorry again for running over time.